Thanks everyone for being here. Today I'm going to be talking to you about creating a simplified geologic map of the world. But before I get to that, since this is my first NACIS conference, I wanted to just give you a little bit of background on myself. Like Hans said, my real job is working for a company called Interflu. We specialize in dam removal and river restoration projects, and so I get to do a lot of fun work for them, everything from in the field work to a couple GIS cartographic projects every now and again, and then also helping out with construction as well. And then as a sort of COVID side project, I set up my own company, freelance business, whatever you want to call it, so that I can just make more maps. And today I'm going to be telling you about how I created a simplified geologic map of the world, starting out by just explaining what is a geologic map, giving a brief history of geologic mapping around the world, talking about modern geologic maps, the need for a simplified map, and then finally getting to how I created the map itself. So what is a geologic map? A geologic map is simply a map of the distribution of materials on Earth. It uses colors to show rock type and age, and symbols and lines to show other geologic features. And the intent of these maps is typically to show the geologic history of an area. Getting into the history of geologic mapping to help you better understand what they are. The oldest geologic map, in my opinion, is what's known as the Turin Papyrus, created in about 1150 BC, and depicts Wadi, a dry river between the Nile and the Red Sea. It uses colors to show different rock types, in this case granite, which the ancient Egyptians would mine to build their various megalithic structures, as well as gravels of different sizes within the riverbed itself, which was a resource that was in short supply in ancient Egypt. Now, like most of science, we're going to just skip the next 2,500 years until we get to the Renaissance and the Age of Discovery, when the Europeans started exploring the world and mapping it in increasing levels of detail. This is one of the maps from that era, one of the earliest maps, and a really cool map because it does attempt to show the Earth in 3D. So on the top of the screen here, we have a little mining village, and then below that we have the various mine shafts going down and showing those miners mining the ore from those veins. And if we zoom into the bottom here, we can see a couple miners doing their work, and the vertical stratigraphy of that area is stratified as hanging rock, cleft ore, and lying quartz. So we have a recognition of a vertical layering within those different rock layers. Moving on into more of the mid-1700s, we have some very good French cartographers working in the area around Paris. And so on the left side of this image, we can see a bunch of different symbols. If we zoom in on that and do a rough translation of a couple of those symbols, we can identify little red squares are building stones, and the curly Qs are gem quartz deposits. So we can zoom in on the map itself and identify where some of those resources are located in the area around Paris. And then on the right, we also have another vertically recognized stratigraphic column of the different rock units within that area. And so these are some examples of early geologic maps. They're generally regionally focused on a very small area, as well as tending to have a more economic focus. And that wasn't the paradigm until William Smith came along. William Smith is a very famous geologist and cartographer who's recognized as making the first geologic map. His life story is absolutely fascinating. There's a wonderful book on it called The Map That Changed the World. He was more of a blue-collar worker, and he was actively snubbed throughout his life by the Geological Society of London. His day job was surveying coal canals. So in England at the time, they would use canals to transport coal from where it was quarried and mined to where it was needed to be burned for fuel and power. And so his job was making detailed surveys of these areas. And while doing this, he started to notice different fossils that he kept finding in the same stratigraphic location, in the same kind of rock units. And he started using these fossils to correlate identical rock units across vast distances, in this case, the whole of England. And so that's how he began his life work of creating a geologic map of England, Wales, and parts of Scotland. And so that's the map on the right here. And if we zoom in on that, we can just see the absolute level of detail he was able to achieve with this simple method of using fossils, with the various colors used to depict the localities of various rock types across the whole of England. And then we also have a simple cross-section showing the transition from the oldest rocks in the Highland of Wales to the youngest rocks in the Valley of the Thames. And so this method of detailed geologic mapping quickly spread throughout the whole of the world and led to the modern geologic maps we see today. So I'm just going to give a brief example of a modern geologic map, in this case from the Minnesota Geological Survey, which is making some of the best geologic maps out there, in my opinion, but I'm a little bit biased since I'm from here. So this is their map of Hennepin County, where we're located. The little red dot right here is about where downtown Minneapolis is. And we can see two maps here, one depicting the Quaternary geology, so the various gravels and sands that the glaciers deposited as they moved over this landscape. And then buried beneath that, we also have a depiction of the bedrock geology that was laid down in the ancient seas about 200 million years ago. Then there's more detail. We're getting into the depth, the thickness of the various layers, and a depiction of how those wax and wane across the landscape. And then we're also showing where different materials are, in this case sand deposits, which are very important to aquifers and various groundwater resources. And these maps exist at the county scale, at the state scale, and all the way up to the continental scale. But they're all typically complex and very difficult to read. They're scientifically super dense, and they're intended for a professional geologist. And so that's a problem when your intended audience is middle school and high school students. And so that's the problem that the Concord Consortium found themselves in while they were developing their learning module called TecRocks. TecRocks is a super cool learning module, online, interactive, and it's to teach the tectonic rock cycles and link that to the formation of various rock types, with the intended audience being middle school and high school students. And as part of this, they have this really cool interactive learning module where students can go in, they can draw various continental and oceanic plates, and then they can run those plates together, they can collide them, and they can go in and see the various rock types that are developing, as in this case, an oceanic plate is running into a continental plate. And so they wanted to show some real-world examples of this, but they went out, they started to look for geologic maps, and they quickly realized that all the maps out there weren't really at the level of detail they needed. And so they contacted me, and they tasked me with the seemingly simple task of creating a simplified geologic map of the world. So to do this, I went out and gathered the data. I had to process it, obviously. I created a number of static maps and then also an interactive map. So in gathering the data, there's a bunch of really good online resources. One of them is called One Geology, which just has a whole variety of different geologic maps from all the different geological surveys around the world. We also have MacroStrat, which uses similar data layers, but just has a much cleaner interface to it. The Canadian Geological Survey has a pretty good, very detailed geologic map of the world. And then we even have a more detailed map of the world within this global lithological map database. Ultimately, after scouring the internet, I ended up using these two data sources. One's a 2005 data source that I used for all the areas on the land, and then I also pulled another data source so that I could depict the rock types beneath the oceans. And I chose these because they seemed to balance simplicity and detail, and they had inherent rock typing that was similar to what we wanted to use in the learning module. So this is that 2005 database that I used for areas on the land. And as you can see, it's pretty complicated in itself with a number of different types and scientific naming conventions for all the geologic units. For the areas under the water, I used what was called a geomorphology database. So it's actually depicting land types, land forms, but I was able to interpret that to get a rough idea of what different rock types were. And so I took this source data, pulled it into GIS, simplified it, combined it, and then finally created the maps. I broke the data down into these 8 layers, so oceanic and continental sediments for all the unconsolidated gravels and sands, sandstone and limestone for the sedimentary rocks, metamorphic rocks I just lumped into one category, and then broke the volcanic rocks into granites, andesites, and basalts. So now finally onto the maps, because I couldn't really just make one. This is my global rock type map showing areas covered by oceanic sediments, areas of basalt, and the various other components. And so based on this data, I was able to also make a number of regional maps. And so with this, we can look at the continental cratons, so the hard crystalline metamorphic rocks that form the center of most of our continents. We can see what happens when 2 continents are colliding together, here in this case with the Himalayas and all the metamorphic rocks that are forming because of that collision. We can look at a more complex continental convergent boundary, such as where Europe and Africa are colliding into each other. We can see all the basalts that are forming as continents are ripped apart in the case of East Africa, or as oceanic plates are ripped apart here in the mid-Atlantic. We can see that andesites start to form as 2 ocean plates combined, such as on the Aleutian Islands, or in the southern Pacific Ocean, where again we have 2 ocean plates combining, forming those andesitic rock types. And then as oceans and continents start to collide, we start to see more granite rock typing forming, such as here along Patagonia in the Andes, or along the Pacific coast of Canada, where again we have a lot of granitic rocks starting to form. So I was also able to build an interactive map based off the Terra.js platform. And so with this, assuming it all loads accurately, we can zoom around the globe and see the different rock types along the different areas. And the reason I chose this platform is because we can also switch that to 2D for students that maybe don't have as high of an internet connection, but still want to access the data. And so with that, thank you. Yeah, up until fairly recently, it's been a guess. Obviously, with geophysical methods, we can start to actually see what's going on. With the oil and gas industry, they do a lot of really deep boreholes, so we can get a sense of different geologic layers, and then it's all interpolating between those fixed points where we actually have data. There's an increasing desire, especially in the last 5-10 years, to make full 3D geologic models. And so the Minnesota Geological Survey has been leading a good portion of that. It's just the surface.
What's at the surface?
Yep.
Does the surface mean down 100 feet or 1,000 feet? Or?
You know, at the level of detail I'm working at, I don't know, and it doesn't really matter since the intended audience for this is, you know, middle and high school students. But that's like an excellent question and something geologists think about a lot.
Yeah, I was curious, have you thought about doing another simplified map of structural features like faults or, plate boundaries, that other side to, basement?
Yep. So that's something I'm working on adding. Right now in the interactive map, I do have the plate boundaries, which are these bright blue lines snaking through. But yeah, faults and everything else is something that could be added as well.
Yeah, I guess last thing I wanted to ask about that is like, do you think that is interesting to this demographic? Like, I don't know, like,
Yeah. Within this learning module, it's probably not going to be addressed, but that's something that, you know, a separate learning module could be developed for to discuss how those faults interact. Because obviously it's hugely important if you live on one of those faults to know what could happen if the ground decides to move. Yep. Cool.
Thank you very much, Sean.